Hello and welcome to this exciting course on time and space complexities. My name is Kamal Rawat and I will be your instructor for this course. Before moving further in the course, let us try to figure out what is it that we want to achieve with this course. After completing this course, you will be able to find the time and space complexity of any function or any piece of code or any algorithm. For that matter, you will be able to solve the big O, small o, big O, omega, theta, all of these asymptotic equations. Our aim is to find a method to measure the time complexity and the space complexity of any piece of code. We want to do that because if we know how much time or how much extra memory a piece of code or an algorithm is taking, then we will be able to measure the effectiveness of that piece of code. And if we know the effectiveness of a piece of code, then we will be able to compare that piece of code with another piece of code solving the same problem. The effectiveness of an algorithm is measured on usually these two parameters, time and space. You can say that maintainability can also be one factor. Yes, it is. But maintainability is not about effectiveness of the code. Maintainability is about how good or how readable the code is so that it becomes easy to maintain or easy to understand. When we say a code is taking resources, there are only two resources. One is the time. Time means the CPU time to execute, and second is the memory, which is usually the RAM. These two parameters, time and space, are super important. Another parameters, as I said, is maintainability of the code, and sometimes there are practical considerations like how much time will I take to write that algorithm. Let us say there is a very effective algorithm, but I don't know that algorithm, or I will take a lot of time to write that algorithm. So sometimes we take the easy route and write the not so optimal algorithm. So these are real life considerations. These will not be factors in an interview, and these will certainly not be factors in the GATE exam because they are not measuring the effectiveness of the code. For the effectiveness of the code, there are only two parameters, the time taken by the code and the space or the extra memory taken by the code. Now, before moving further, let us take an example. Consider the piece of code written in C++ language. So this is a simple for loop which is running n times, and every time inside the for loop, we are just printing hello. If I ask you how much time will this for loop take to execute, you will probably need more input. You will ask questions like, what is the configuration of the machine in which we are running this code? What is the hardware of the machine like? How much RAM is there in the machine? How many different processes are running at a particular time which are keeping the CPU busy when we are trying to run this code? Because if there are a lot of other processes which are running at the same time, then there will be context switch and this piece of code will be slower. So it will be difficult to come up with an absolute time taken by this for loop to execute. Why? Because we need more details. We need the hardware details of the machine. We need the configuration of the RAM. We need the motherboard. We need the state of the machine at that particular time when this piece of code is running. And you also need the absolute value of n. And even if you are able to come up with the absolute time for a particular machine and for a particular state, then also that time will be useless because you will not be able to conclude anything from that time. You will not be able to conclude how much time is this for loop taking. What we are interested in is the time taken by this algorithm, not this algorithm on a machine. So how can we come up with a number which gives me the time taken by only this for loop, irrespective of the machine in which we are running this for loop? So that time will not be absolute time. That time will just be a proportional time. So what we are interested in is to find a time that is proportional to the input. So find the time taken by this algorithm or this piece of code proportional to the input. Now, how much that time can be? Let us see the total amount of work that we are doing. First of all, we are having this initialization. Let's say this initialization is taking time t1. Then we have this condition check. Let's say this condition check takes time t2. Then we are printing this hello. So printing hello will also take some time. So let's say the printing hello on a particular machine takes time t3. Then this I++. So increment will also take time. Let us say the time taken to increment I on a specific machine is t4. On that particular machine, the total time taken by this for loop will be t1 plus t2 plus t3 plus t4, and this will be n times because the condition will be checked n plus 1 times. So you can say that t2 will be added n plus 1 times. Time taken to initialize, time taken to check the condition, time taken to print, time taken to increment, these times will keep on changing for a particular configuration or for a particular state of the machine. What will not change is that this formula will not change. This formula will remain the same. So I can say that, let's say T2 plus T3 plus T4 is T5 and T1 plus T2 is, let's say, T0. So I can say that total time taken by this for loop for n is equal to T0, that is equal to T1 plus T2 plus n into T5. If we want to mention this time in proportional terms, then we can say that total time taken by this for loop for a particular value of n is directly proportional to n. So we ignore the constants and keep n. So when we say that total time taken by this for loop is directly proportional to n, it means that as n increases, the time also increase, and as n decreases, the time also decrease. So this for loop takes linear time with respect to n. This is what we can conclude. Now this time does not depend on any machine. This is the time of this algorithm, this piece of code only. When we say Tn is order of n, we will come to the order complexity later, but if we say Tn is order of n, it means that the time taken is proportional to n. Time taken by the algorithm is proportional to n, and we have removed the machine from the picture. This time taken is only the time taken by the algorithm irrespective of the machine. So no matter what the machine is, this for loop is going to take the same time. If it is a slower machine or older machine, then these constant factor will be high. And if it is a newer machine or a machine with a higher configuration, then these constant factor will be low and the total time taken will be less. But the variation of the time with respect to n is going to be linear only. If you plot it on a graph, this is the value of n and this is the time taken. The time taken by the function with respect to n can go like this for a particular machine. For another machine, the time taken by the function can go like this. For yet another machine, we can say that time taken will go like this. So this is a slower machine, this is a faster machine, and this is the fastest of the three machines. The thing that is common in all of these three is that all of these three are linear. They are straight lines. So we can say that all of these three lines on the graph represent the linear time and the constant factor are changing. You know that merge sort takes n log n time, quick sort also takes n log n time, and heap sort also takes n log n time. Their proportional time taken is the same, but their actual time taken will be different because their constant factors are going to be different. So when we compare the effectiveness of merge sort, quick sort, and heap sort, those comparisons will not be on the proportionality of the time because the proportionality of the time is same. Those comparisons will be on the constant factors. That is also important, and we will come to that in the later sections of this course. This proportional time taken by any algorithm is called the asymptotic time or the time complexity of the function. So we can say that the time complexity of a function is not the actual time taken by the function, it is the proportional time taken by the function. I'm sure you know the algorithm of linear search. Let us write the code for linear search. So this is the function for linear search. This function receives an array and a value. It searches for value in the array. If the value is present in the array, then this function returns true. Otherwise, this function returns false. This piece of code is in Java. If you look at this function is nothing but an iteration, but a traversal of the array. So it is going to each and every element of the array, and for every element, it is comparing whether that element is equal to the value or not. If that element is equal to the value, then it is returning true from there itself. Otherwise, when the entire traversal of the array is complete, when we are done checking each and every element of the array, then at the end we will return false. The linear search effectively means going to each and every element of the data structure and comparing that element with the value that we are looking for. If the element is equal to the value, then we suspend our search and return success from there. Otherwise, we continue the search till the end of the structure is reached. When the end of the structure is reached and if the value is not found, then we will return failure. Now, the time taken by this function depends on all the previous things that we have discussed. It depends on the length of the array. It depends on machine configuration that we have learned to ignore. But it also depends on where value is found inside the array. Let us assume the array to be 5, 1, 2, 4, 3, 6. if you are looking for value 5, then 5 will be found at the very first position in the array, and this loop will iterate only once. While if you are looking for 6, then this loop will iterate every element of the array till it reaches the end of the array, and when it reaches the end of the array, then from there it will return success. So the loop will iterate n times. If you are looking for, let's say, 10, because 10 is not present in the array, again the loop will iterate each and every element of the array, and from the end it will return false. So again it will take n times. So we can say that the minimum time taken by this function is when the value is found at the very first position, and the maximum time taken by this function is when the value is either not found or found at the last location. The time taken by this function depends on n, which is the length of the array, but it also depends on where the value is found in the array, if it is found. If the value is found at the very first position, then the total number of statements that gets executed will be constant. This statement will execute, then initialization will happen, then condition will be checked, and then this condition will be checked. This condition is true, so we'll just return true. If the value is found at the very first position, then we are executing only 5 statements inside this function. So 5 statement means that we are executing constant number of statements, so it does not depend on the length of the array. So we can say that time taken is directly proportional to some constant, or 1, directly proportional to 1. But if the value is found at the last position, the time taken will be directly proportional to n, means some constant into n. In the best case means when the function is taking minimum time. So in the best case, the time taken is constant, and in the worst case, the time taken is proportional to n or linear. Which of these two times do you think is more important in the industry? Let me give you an example. Let us say you want to give the contract of building your website to a company. You want the homepage of your website to be loaded in 1 second. So what will be your condition to the company? Will you say that the homepage of the website should get loaded in 1 second in the best case, or will you say that the homepage of the website should get loaded in 1 second in the worst case? You will probably go with the worst case. Why? Because the best case happens only once. Maybe that company can show you that, okay, so this time the homepage of your website is getting loaded in 1 second. We have shown it to you. We have shown the best case. Now it is yours. On the other side, if you have negotiated that the homepage should not take more than 1 second in the worst case, then it is a much tighter negotiation. Now for every situation, the company will have to ensure that the homepage does not take more than 1 second to load. So in the industry, the more practical time complexity is the worst case time complexity. That's why whenever we say linear search takes order of n time, we are not talking about the best case of linear search, because that is what we are not interested in. What we are more interested in is that linear search should not take more than order of n time, more than linear time, more than time that is proportional to n. During the interview, the interviewer will be more interested in the worst case time complexities of your algorithm than the best case time complexity of the algorithm. Because best case can be corner case, you can just put a condition in the top, and for that condition it is running in the best case. So that does not show every aspect of the algorithm that you have implemented. Every aspect of the algorithm will come only in the worst case. So for every algorithm, we can talk about the best case time complexity, we can talk about the average case time complexity, and we can talk about the worst case time complexity. But in most of the situations, you will be interested in finding the worst case time complexity, and the worst case time complexity of the algorithm is given by the upper bound, and the upper bound, as we will see, will be given by big O notation. So when we say linear search takes big O of n, it means that we are talking about the upper bound of the worst case. We will learn about the upper bound, lower bound, and theta bound in the subsequent videos in this course. Practically, for most of the algorithms, the average case time complexity is as worse as the worst case time complexity. So that's why the average case time complexity gets ignored. For linear search, the best case time complexity will be 1, the worst case time complexity will be n, and the average case time complexity will be n by 2. And as you know that we ignore the constants, so the average case time complexity again comes out to be n. So the average case time complexity asymptotically is as bad as the worst case time complexity. To sum up, the time complexity of an algorithm is the number of steps of that algorithm which are getting executed. and not equal to the actual time taken by the algorithm.